Hey, good afternoon. My name is Jon Stork. I work in the Materials and Research Division here at the North Dakota Department of Transportation. I've been asked to give a brief update on our ongoing research activity regarding the density profiling system. So, our ultimate goal for the system is to reduce or possibly eliminate the need for destructive coring on our new asphalt roadways. So, by utilizing this type of technology or similar technologies during construction, we can obtain full coverage density in order to identify issues in the construction laydown operations and to fix them before they become an extensive and expensive issue requiring penalties or rework. So why do we need continuous density measurements? Well, it all comes down to quality and dollars. So we spend over $100 million a year on our hot mix construction program. And so we have an obligation to construct these projects to the best of our ability in order to maximize the service life and minimize the amount of preventative maintenance activities that impact the traveling public. So by utilizing this technology and other complementary intelligent construction technologies, we can be confident in the product that we are buying and ultimately move towards reducing coring numbers, which will save both time, money, and increase safety on our projects. So just to preface what we've done with this research so far, we joined this effort back in 2020 by teaming up with other state and federal agencies, contractor equipment vendors, software vendors as part of a national pooled fund effort regarding this type of ground penetrating radar technologies. What this means is there's many different agencies and people across the country that are contributing time, effort, and dollars into finding a better way to measure density because we know that it is a proven performance metric in the quality of our pavements. So to do this, we've deployed this technology on over 15 mixes across the state with varying aggregate sources, wrap percentages, different gradation compositions, different binder types, different construction methods such as joint configurations, lift thicknesses, seasonal temperature ranges, admixtures, rehab strategies, all that sort of stuff. So all this research has given us insight and confidence into the possibility of pushing this technology towards implementation on our network. So how does this technology work? Quite simply, it's a ground penetrating radar system that uses composite dielectric readings to measure the composition of the asphalt mixture. So you think of the main components in an asphalt pavement. You have your physical aggregates, you have your liquid binder, and your air voids. So for the sake of explanation, they all have a dielectric value. So we consider the proportions of aggregate and binder fixed. And so those dielectrics are fixed, and the only thing that changes from here to, let's say, 200 feet from here is the amount of remaining air voids after the rolling train has completed. Now, obviously, the main cause of that is the changes to the compactive effort that's imparted on the pavement or from varying levels of physical segregation, thermal segregation, other things that can be going on, material changes, all sorts of that stuff. So using this, the dielectric that we're predicting, we can then convert to a density in real time across the entire surface of the roadway. So there are some limitations with this type of technology. The frequency that's imparted on the pavement is only measuring about 2 inches into the surface lift, and we're scanning beneath, directly under the antennas for about a 6-inch diameter. So we're able to, with a 3-pass configuration on a standard driving lane, we're able to get about 50% coverage of the pavement. Now, it's not exactly full coverage as the name implies, but the distance between the scan lines is about 2 feet typically, and it allows us to basically determine the uniformity across the mat transversely and determine the conformance to our specification at a much greater confidence than our current random coring frequency of 1 core per 1,000 feet, to which we assume this core is perfectly representative of the entire sublot and we pay off of it. So as we'll look at a little bit later, there can be large amounts of variability depending on the construction methods. So Here's a few photos of the current configuration of the field and laboratory setups. The top is, you can see the 3 antennas on the push cart. That is currently how we're still collecting. Those can be adjusted for varying lane widths. The lab setup on the bottom left is an important improvement in the last couple of years. It allows us to measure the gyratory specimens at the asphalt plant, and they're already fabricated as part of the QC/QA process, and we simply scan them before we dunk them for bulking. It allows us to track the dielectric changes, basically how the plant mix is changing as we adjust aggregate blends, binder, wrap percent changes, all that sort of stuff, and then all of the other volumetric properties. So that's important to know when you're out in the field scanning, is if you see a change at the plant, you'll see a change in the field. So photo on the right is what the operator is seeing in the field. Top portion and bottom portion are both the same data, they're just displayed a little bit differently. The top is sort of a heat map across the 3 antennas, and the bottom is a linear representation. So if you look at the screen, you can see a little red blip on the top of the heat map on the left sensor. That's an area of high density. And then you can see a blue a little bit further down in the stationing on the right sensor. That area, that indicates an area of low density. So same thing on the top and the bottom. You can see those blips in a linear format. The equipment is also equipped with GPS and distance measuring capabilities. So it allows all of this data to be processed and overlaid into a spatial environment, such as Google Earth, or we use Veda, which is kind of a program that allows for the addition of different file formats across all the IC technologies, and it allows them to be standardized into one program and compared against each other for that. So definitely a powerful tool for that. One of the large research activities that we completed in the last year was to assess variability and sensitivity of this equipment and on the dielectric readings across an entire project. So this is important because we wanted to determine the frequency of calibration activities moving forward and assess the viability of the dielectric determination across subsequent days and weeks of paving. So what that really means is, do we need to calibrate, every 1,500 tons as we test? Do we need to calibrate once a day? Do we need to calibrate once a week or once a project, or anytime something, we're looking at how those different mix changes affect the dielectrics and the calibrations, because that's ultimately what affects your accuracy as you predict the density based off the dielectrics. So we're also able to assess, how the different weather conditions, temperature affects it, how the joint layouts affect it, subgrade, subcut locations, all that sort of stuff, if it has an effect on the dielectric of the pavement above it. The selected project was North Dakota 6, from the junction of North Dakota 21 to the BIA 7. It was located in Morton and Sioux counties and took place in the Bismarck district. So this was a 19-mile job. Had 60,000 tons of RAP 42 and a standard 58S-34 binder. This was also selected because it had IC rolling, it had paper mounted thermal profiling, e-ticketing, it had a ride spec on it, and it had the longitudinal joint SP at the time. So we typically try to pair the DPS activities with these other IC as they complement each other, and we can get sort of a full depth and comprehensive look at what's going on with the pavement and what causes the density numbers, whether they be good or bad. So I'm not going to go too far into the project data and the specifics of it, but I did want to share just some of the few highlights from the full coverage data that we found. So we collected about, it was over 200 miles of cart data. This graphic here shows it's basically 11 feet wide. This is the main line, so we exclude the joint out of this data, but it's 100-foot sublots, and so it's showing about a little over 13 miles of the 19-mile project. This is the top lift, and it shows both the northbound and the southbound lane. You can see most of the The segments here fall well above the 91% minimum denoted by the black line. Overall, the mainline densities for this job were, well over 94%, and contractor did a really nice job on the construction. We did have a couple areas that you can see fell below the 91%, and that's, I guess, what we're trying to figure out the cause of that and what went wrong in those areas, because they're not a single foot. These are, as I said, 100-foot segments that are full width, and so there's a little bit of area there for improvement. Here's another interesting finding on this project. This is something we wanted to look at, was the comparison between the confined joint and the unconfined joint and how that showed up within the DPS data. So the blue is the joint left and the orange is the joint right. There is a little bit of flip-flop between which one was the confined versus the unconfined, because just the way the paving operations went, they hop back and forth a little bit just to match up. But you can see the lower density one is significantly lower, and that is the unconfined when they're matching up to the previous day's paving. So typically when we're doing the notch wedge, as we had on this job, when we take the core, we're taking them within the middle of the notch wedge. And so what that does is it averages out the two lanes. But when we're scanning with the DPS, we're able to pick up the differences between these lanes because we scan on either side of the vertical faces of the wedge. So obviously that's an important thing to know, is the difference between them. We found probably a 4 to 5% difference between the two lanes on average. So it's an important thing to know for research purposes. There's preventative measures such as milling and paving only one lane at a time, or cutting back the areas of low density to minimize longitudinal joint raveling in the future. That could be implemented if we have issues with low density on the matchup lane or on the unconfined lane. Here's just a breakdown of a few core locations that we use to validate the DPS data. Now, when I say that, basically what we're doing is when we're on the road, we're scanning, we'll take a static measurement of the core location, we'll extract them, we'll bulk them out, and then we'll compare it back to what we predicted the density to be. That's just sort of a data validation tool that we use to predict to assess the accuracy of the equipment. Now, when we say we're going to go coreless, this would probably still have to be done for data quality purposes, but it wouldn't have to be done at 2 in the morning to cut all the cores for the previous day paving for acceptance purposes. So definitely some differences there. Another thing you can see out of this graphic is the variability that occurs within the paving operations. Depending where the acceptance core fall, there could be a pretty big difference between if you fall in the blue versus the green. There's like a 4 or 5% difference there, and you'll see a big difference in both the pavement and the quality of the pavement. Here's another example of other IC. It's the IC rollers compared to the DPS data. So what we're comparing here is the number of passes versus the in-place densities. This is, obviously very, very powerful tool when we're talking about setting up rolling passes and rolling patterns. This one was done, this wasn't on Highway 6, but this comparison was done after the project was completed. But there's definitely been instances where we've been able to, catch this right away and talk to QC or talk to the rolling guy and make these changes in as close to real time as possible, to where we can avoid having these areas of non-conformance for an entire day or an entire project altogether. So this is definitely a major effort of the pooled fund, is to make this data usable and to make it as real time as possible, so that the QC process control or the paving superintendent, the roller operators, all of those people can see what we're getting while we're scanning, in order to make these changes so that we have a better finished product, instead of simply using it as a forensic tool. We're not looking to say, gotcha with this. We're looking to use it to better the quality of the process. So the tough part of this is, how do we take, these millions of points and all of this thermal data and all of these, these IC data, and how do we make useful changes to the program. And so that's one thing. That's kind of where we're at as an agency, is we're going to continue this research with the DPS data. We're going to continue to be a part of the pooled fund on the national level, and we're going to continue to collect information. Like I said, we're hoping to go to a vehicle mounted solution here, as shown on the screen. It's something to where we can have, you know, less of a safety concern. Currently, safety is a big concern when you're walking in live traffic. Sometimes you're pushing, you know, a cart going away from the people coming behind you, and you got, you know, construction traffic and traveling public. It can be night paving, you know, it can be a big safety concern. And then it's also the labor intensive nature of some of this. You're walking, you know, on this one 20-mile project, 2 lifts, 2 lanes, 3 passes. I mean, it's 200 plus miles of walking. We have 8 districts, we have 1 unit, and we have many construction projects that are going at the same time. So there's some barriers to some of that. If we can, there's a lot of people working on it, whether it's, you know, the vehicle mounted system that is going to be commercially available shortly. There's the bottom left is a robotic unit that runs off an alignment file, gets the operator out of the equation completely, you know, so that's an option. There's work being done on the roller mounted process to have that be a seamless integration into the rolling train. That would be probably the ideal thing. But there's a lot of people that are trying to overcome these barriers for the collection methods. One other big thing that we're working on in the pooled fund is how to navigate the intricacies of what is needed to use this type of equipment for acceptance, while still satisfying the Code of Federal Regulation requirements for acceptance of construction materials. So that's something obviously that's necessary for us when we're using this on a federally funded project. So that's something that needs to be overcome before we start pushing this for acceptance purposes. So overall, NDDOT sees a large benefit in using technologies such as this, and we will continue to pursue this towards the implementation for density acceptance and the coring reduction in our hot mix programs. So I've shared my contact information on screen. Feel free to reach out with any questions or concerns or feedback, and I thank you for your time.